Thank you all for coming. It's a real honor to be giving this Lise-Meitner-Lecture, and particularly timely to be presenting it on International Women's Day. I hope to be able to maybe in some small way remind young people of both genders that it's okay to become a physicist. So this is a picture of a piezo force microscopy image of the surface of a multiferroic material. The black and white represent opposite orientations of electric dipole moments. And I've embedded it in a picture of the cosmic microwave background from the Hubble telescope. And over the next 40 minutes or so, I'll explain to you the connection between these two pictures and how physicists are using both of these properties to try to answer the same kinds of questions. But first I want to start with a quiz. So on the screen are two computer simulations. One is a simulation by Martin Kuntz at the University of Geneva of the formation of cosmic strings in the early universe. And the other is a simulation by Thomas Lottemasser at the ETH of the formation of the intersections between those electric dipoles, the regions of opposite electric dipoles that I showed you in the previous slide. And take a look at these two images and see who can tell which is which. I'll give you 30 seconds. You may talk to your neighbors, and we'll take a vote. Don't worry about the funny surface on one. It's just that one of the two scientists were a little more artistic. Okay, so votes for cosmic strings on the left, cosmic strings on the right, and who really can't tell? Very good. So actually you're correct. So these two simulations mathematically are simulating an identical symmetry lowering. And it's this fact, the fact that the phase transition that's proposed to have given rise to cosmic string formation in the early universe has the same symmetry, it has the same mathematical form as the structural phase transition in our multiferroic. It's going to allow us to use one to study the other. So in fact, the one on the right is the multiferroic simulation of a material grown in my laboratory at the ETH, but mathematically you can't tell the difference. Okay, so let's start at the beginning with the Big Bang. And in particular, with what cosmologists believe happened in the early universe just after the Big Bang, as we moved from having completely homogeneous vacuum to having some structure in the early universe. Do I have any cosmologists in the audience? Okay, so there's no one to keep me honest. I should give you a little disclaimer that all I know about cosmology I learned from kind colleagues over the last couple of years, but I hope I don't tell you anything actually incorrect. So here's kind of the standard model of cosmology. From the Big Bang, we know that the universe, as time evolved on this axis, the universe cooled and it lowered its energy as it expanded. And each of these lines cutting across this diagram represents a phase transition, a proposed symmetry-lowering phase transition that cosmologists hypothesize occurred during the evolution of the universe. And of course, some of these have rather some experimental support or observational support, and some of them are much more speculative as one goes back further in the history of the universe. And in particular, I want to focus today on this proposed phase transition here, which is proposed to have occurred 10 to the minus 37 seconds after the Big Bang, and which is important because you'll notice on the left of this transition, these wiggly lines are just photons, and on the right, we start to have our first particles. So this phase transition, called the grand unification transition, is one of the proposed mechanisms by which mass was able to form in the early universe. Okay. So this is a public lecture. I developed this lecture for bachelor students and school students. Do we have any here? Okay, this is for you then. So I apologize if it's a bit elementary for many of the professionals here. But the symmetry lowering phase transition, which is proposed to have occurred in the early universe, is maybe for some of us a little of an unfamiliar concept, but one can think of it as being somewhat analogous to the freezing of water to form ice. Water has high symmetry because the molecules are all jiggling about, and so whichever direction we look in, we see exactly the same thing. We see randomness. Whereas ice has lower symmetry because the molecules line up, and so when we look upwards, we see something different than when we look to the side. So the symmetry is lowered. And even for the experts, I want to point out an important aspect of symmetry lowering phase transitions that at least I think sometimes we don't always think about. And that's that associated with a symmetry lowering phase transition is the formation of defects. And again, I'll illustrate this with the freezing of ice out of water. This is a photograph from Antarctica of the formation of ice platelets on the surface of a lagoon. And you can see at the start of the ice formation process, different regions of the lagoon surface form different platelets of ice, and the molecules in these different platelets can have different orientations relative to each other. So that when they come together, you see this, or hopefully you can see this, in the light's not so great here, when they start to come together, as in the front here, when one platelet meets with another platelet, at the point where they intersect, one forms a defect, where the ice molecules from one platelet are not aligned in the same orientation as the ice molecules in another platelet. Here's another image of that where the ice is frozen up more, and I've put these arrows just as a possibility of the different orientations of the ice molecules in the different platelets, and you can see the defects that form when they come together. I thought it was quite fun that these ducks decided not to sit on the defects. They like to sit in the middle of the platelets. This picture is in Stockholm, not in Antarctica. So this defect formation at symmetry lowering phase transitions is going to be the aspect that I'll be focusing on today. So back to the early universe then. In the early universe, rather than having liquid water going to solid ice, the proposed change in the state of the system is that one had a homogeneous vacuum, a vacuum that is identical in every direction, just like the water, making a phase transition to a lower symmetry vacuum, a vacuum that has lower symmetry, that has an orientation, if you like. And again, this is a hypothesis, but the proposal becomes even more specific than that. The proposal is that this symmetry lowering phase transition is described by what's called a Mexican hat potential, which is something that I think all physicists have encountered in some form or another, because it's a rather ubiquitous kind of potential in physics. What it means is that before the transition, when the system's in the homogeneous vacuum in the high symmetry state, its energy is sitting up at the top of the hat, and in every direction it looks, it sees the same thing. And after the phase transition, the system drops down to the lower energy phase, somewhere in the bottom of the hat, in its lower symmetry vacuum. But it can have any orientation. It can adopt any of these positions in the brim of the hat. In case you're not so familiar with thinking about phase transitions described by Mexican hat potentials, I want to tell you or remind you of a story. How many of you know of the story of Buridan's donkey? Not so many. This is a beautiful story. So Buridan was a farmer, and he had a donkey, and the donkey was hungry, and Buridan took him into a field which had bales of hay, but unfortunately, Buridan placed the donkey right in the middle of all of the bales of hay. And the donkey, he was at a high high hunger position, I guess, rather than a high energy position. He had a high degree of hunger. He wanted to drop down into a low hunger state somewhere around the rim of the hat and eat the bales of hay, but he couldn't decide which direction to go because all of the directions were equivalent, and faced with so much choice, he got stuck. He stayed in the center. He actually died of hunger. So the early universe did better than Buridan's donkey. If Buridan's donkey had been smarter, he would have realized that he could have gone in any direction, that it doesn't matter, that he could have lowered his hunger by moving towards this bale of hay or towards this bale of hay, and he could have, in fact, adopted any of these symmetry equivalent low hunger states, and he would not have starved to death. So the process by which the universe makes this grand unification transition, you can think of as kind of an intelligent Buridan's donkey. Instead of staying up in this hungry state at the top of the hat, this high symmetry state where it remains hungry, it drops down into any of these low symmetry states with equal probability, and it lowers its energy, or in the case of the donkey, it lowers its hunger. So the picture then in the case of the early universe, as it proceeds through the grand unification transition, of course, different regions of the early universe choose different ground states, just like different regions of the surface of the lagoon crystallize the ice with different orientations. So in one region of space, over here, kind of geographically, the vacuum would lower its symmetry with one choice of angle, which would be random. In another, it would adopt another choice of angle randomly, and in another, it would adopt another choice of angle. So as the universe starts approaching the phase transition, these low symmetry regions start to fluctuate out of the high symmetry vacuum, and as the system crosses the phase transition, these regions grow and they grow, and eventually they meet, and the entire system is in the low symmetry state, but with different choices of angle. So we end up with a defect somewhat analogous to the defects between the crystalline plates of ice, but in this case, the meeting point between vacuum regions with different angle, rather than being a kind of line between the plates on the surface, because of the symmetry of the system, is actually required to be one dimension. It's a one-dimensional string, a one-dimensional line defect that contains the high symmetry state, the earlier part of the early universe, trapped in the low symmetry vacuum. And this is what cosmologists call a cosmic string. So this mechanism was proposed by Tom Kibble, who's also, of course, famous from Higgs boson fame. And mathematically, it's also what's called topologically protected. It's a one-dimensional defect, and this topological protection means one can't get rid of it. It's stuck there. One has a line of the very early universe trapped in the low symmetry vacuum. I should emphasize that these cosmic strings are completely different beasts than string theory strings. As far as I know, they have absolutely no connection whatsoever with string theory strings. So this is the proposal. This is a model. This is a proposal for the behavior of the early universe. It gets even a little bit more specific in regard to how many cosmic strings should have formed. And this depends on the rate of expansion of the universe. And it's kind of intuitive. If the universe expanded slowly through the grand unification transition, then a particular region of space can communicate its choice of angle to the neighboring space. There's time to say to the neighboring regions, hey, adopt the same orientation as me because that will lower our energy. And so we get large regions with the same choice of angle, and as a consequence, the defects, the intersections, have a lower density. Whereas if the universe expanded quickly, then there's not so much time to tell the neighbors to adopt the same orientation as myself, and the regions of low symmetry are smaller, and the number of cosmic strings, the density of cosmic strings is higher. Okay, so that's our model. That's our kind of standard model of early universe physics and cosmic string formation. And of course, one would like to know if this is correct. And so how can we go about testing whether this description is appropriate for the early universe? Well, to measure anything in physics, we need to use a probe that's of a comparable energy to the property that we want to investigate. And for cosmic strings, this energy is of the order of 10 to the 15 gigaelectron volts. So to give you a kind of feeling for what this means, a 1 kilometer cosmic string is proposed to have the same mass as the Earth. So if a cosmic string comes by, I guess we're in trouble. We won't have any chance to measure it before we're annihilated. The highest energy probes that we have available, if we want to actively study cosmic strings, the largest hadron colliders, are about 10 orders of magnitude less energetic than cosmic strings. And so it's not an option for us to go to the LHC and try to generate a cosmic string. We're not even close to the appropriate energy scale. So the options that one has are to observe, to look at the universe and see if one can see a cosmic string. And there are very well-defined signatures of how cosmic strings ought to manifest in the cosmic microwave background. And so as observation of the cosmic microwave background becomes more and more accurate, more and more detailed, one can search with more and more accuracy for the existence of cosmic strings. And at the moment, they have not been observed, and so there's in turn a well-defined upper bound on the possible density of cosmic strings that there can be in the universe. So one can't directly measure, one can observe, one can run computer simulations. So here's the second of the two pictures that I showed you earlier from the Geneva group, in which they simulated a vacuum-to-vacuum phase transition described by such a Mexican hat potential, and you can really see the formation of cosmic strings. And of course, this also has advantages that one can also, in the computer, watch how they evolve, how they form, and do experiments on the cosmic strings. But it's a simulation. It's not real life. So what we would like to do instead is to study the grand unification transition in the laboratory. And our plan is to identify a material, a lump of stuff, that has a symmetry-lowering phase transition that's described by the same physics as that which is proposed for the grand unification transition. And that's this spontaneous symmetry breaking concept that we discussed so far, described by a Mexican hat potential. And then we'll do experiments on our material to answer questions about the grand unification transition. Do cosmic strings exist? Do we see the formation of cosmic strings when we make the phase transition, or cosmic string analogs, I should say, when we make the phase transition in this material? Did they form as we think? Is this idea that when I cool more slowly, I get fewer cosmic strings? Is this a correct description? In the laboratory, we can also watch how they evolve, and we can try to measure their properties. So this was the thesis work of a PhD student, Sinead Griffin, who graduated from my group a couple of years ago and is now a postdoctoral researcher, or this started as her PhD. She's now a postdoctoral researcher at the Molecular Foundry in Berkeley. Okay, does anybody have any questions so far that you'd like to ask, or we save them to the end? That's the end, kind of the end of the cosmological motivation for what I'm going to show you. Now we'll start looking at some actual materials. Okay, so where to look? We want to find a material that has a spontaneous symmetry-breaking phase transition that's described by a Mexican hat potential. And one possibility, or one kind of class of materials, one kind of phenomenology that shows spontaneous symmetry-breaking phase transitions, the class of materials called ferromagnets. These are materials with north and south magnetic dipoles. And in a ferromagnetic material, one again has a symmetry-breaking phase transition at high temperature. These little arrows I'm indicating as the magnetic dipoles. At high temperature, in the so-called paramagnetic phase, these are thermally disordered. They point in random directions. And so the system has high symmetry, again, because whichever direction I look, I see the same randomness, so the symmetry is high. And below the magnetic ordering temperature, below the critical temperature, the Curie temperature, the magnetic dipoles line up, and so I have a low temperature and a lower symmetry. So ferromagnetic materials are candidates for symmetry-breaking phase transition. And indeed, we know that ferromagnets form defects when they undergo such a phase transition, and these defects are the domain walls, the regions separating opposite orientations of the magnetic moments. So I've sketched one here. In one region of a ferromagnet, the magnetic moments might point up, and in another region of a ferromagnet, the magnetic moments might point down. And such domain walls, of course, are tremendously technologically important. There's a fringing field associated with the existence of the domain wall, and this is used in magnetic data storage to represent a 1 or a 0 in digital data storage. So here's a magnetic force microscopy image of opposite orientations of the magnetic orientation in a computer hard drive to show you how, as an example of how the data is stored. The ferromagnets are a possibility, but in most ferromagnets, the domain structure is kind of what I've shown you here. The defects form planar walls, and so they're not really an exact analog to the Mexican hat type potential that we're looking for. Another possibility would be a related class of materials called ferroelectrics. And these are materials that, rather than having magnetic dipole moments with north and south magnetic poles, have electric dipole moments with positive and negative charges. And so much of the phenomenology of ferroelectrics is similar to that of ferromagnets. The ferro part here reflects the similarity in the underlying physics. Most ferroelectrics have nothing to do with, they're not at all ferrous. They don't contain iron, most of them. And ferroelectrics also have a symmetry-lowering phase transition associated with the formation of the electric dipole state. And in most ferroelectrics, here's a cartoon, the defect is again a wall, a domain wall separating opposite orientations of the electric dipole moment. So these are kind of good candidates, but most of them are not exactly what we're looking for. So there's another class of materials. Oh, I should also mention that ferromagnets and ferroelectrics tend to be very different kinds of materials. If you think of your favorite ferromagnet, it's probably something like iron. I don't know if anyone has a favorite ferroelectric, but a typical one would be barium titanate. It's a transparent oxide ceramic. And so these are rather different kinds of materials. And there are very few materials that are both ferromagnetic and ferroelectric. But as was mentioned in the introduction, there are some. They're called multiferroics, and this is an area that's been of tremendous interest for me over the last years because it's been very challenging to design materials that are both ferromagnetic and ferroelectric because of the kind of chemistries that promote the two phenomena are really rather different from each other. But we do have materials now that contain both magnetic dipoles and both electric dipoles. They have both magnetic and ferroelectric symmetry-lowering phase transitions. And because of the tricks that we had to play in order to combine these two properties in the same material, they can often have rather unusual symmetry-lowering phase transitions. And so the material that we're going to use, our kind of prototype material for studying cosmic string formation, is a multiferroic. So here's the material. It's a transition metal oxide called yttrium manganite, yttrium manganese 03. It looks like this. This was grown in our lab at the ETH by my senior scientist, Frank Lichtenberg. It looks kind of metallic, but actually it isn't. It's a ceramic. It's a rather good insulator, and it just looks metallic because its band gap is rather small. It's around a 1 electron volt band gap, but it's actually quite a good ceramic ferroelectric insulator. And here's the crystal, or here's a cartoon of the crystal structure. So it consists of planes of positively charged yttrium ions, in green here, that are separating planes of manganese O5 trigonal bipyramids. So this has a manganese, the center of 3 oxygens in the plane with an oxygen on top and an oxygen below it. And these manganese O5 polyhedra they're connected at the corners to each other. So I have a plane of positively charged yttrium and then a plane of this more complicated manganese O5 polyhedra. And what I've tried to sketch here is that these polyhedra, this material undergoes a symmetry lowering phase transition in which these polyhedra tilt around the vertical axis. And they can tilt, shown by these arrows, forwards, to the back and to the side, to the left, in any direction around the circle, with more or less the same energy. So we have a phase transition here that you can imagine just by looking at this cartoon has the kind of Buridan's donkey feature. This tilting can happen in any direction. And so we have a good chance that this will have the appropriate symmetry to be described by the Mexican hat like that. Okay, so let me just show you the same thing in a little bit more detail. Our material is the multiferroic yttrium manganite. Here's its structure at high temperature. It's in the high symmetry phase. The layers of yttrium are completely flat, and the layers of manganese O3 are also completely flat, so they're not tilted. And in this structure, there are no electric dipoles. The positive ions are completely in a straight line. The negative ions are completely in a straight line, exactly evenly spaced from the positive ions. So this is my high symmetry, what we call paraelectric phase, analogous to paramagnetic in the case of a ferromagnet. At around 1000 Kelvin, we have a symmetry lowering phase transition in which these polyhedra tilt, and they can tilt in any direction around this circle. And when they do that, the yttrium ions in the plane all shuffle in the same direction. And because the yttrium ions are positively charged, then the system develops a dipole moment. If you like, all the positive charges shuffle in one direction relative to the negative charges, and the system develops an electric dipole. So we have a phase transition from a paraelectric to a ferroelectric phase. And it turns out that this phase transition is described by something that's very close to a Mexican hat potential. So this is a picture here of the energy as a function of the magnitude of this tilting as I move away from the center, and its angle as I go around the circle. And this is actually calculated using a technique called density functional theory that allows us to really solve the Schrödinger equation for this material. This is not a cartoon. This is kind of as close as one can get to the true potential describing the transition from this structure. Okay, so you might say, well, she hasn't quite got what she's looking for. She wanted this perfect Mexican hat potential, and she's got something which is not quite as good. But I will argue that this is actually a little bit better, because the details, the non-ideality of this Mexican hat potential are what make it possible or straightforward for us to measure. And so here's the Mexican hat potential again. Here's looking down from the top now, and you see that there are 6 minima. For the experts, the symmetry is, rather than U1, it's actually Z6. Each of these minima corresponds to an opposite orientation of the electric dipoles. When the polyhedra tilt in this direction, the yttrium ions shuffle down. When they tilt in this direction, the yttrium ions shuffle up. And so we can measure much more easily these electric dipole moments than we can measure the angle of tilting of a polyhedron. So the fact that we have this extra symmetry lowering to the Z6 symmetry means that our experiments are much more straightforward. It's much more straightforward for us to actually observe what we've ended up with. And so in the picture that I showed you right at the start, the image, if you remember, of the electric dipoles in yttrium manganite, the black and white regions were corresponding to these opposite orientations of the electric dipole. So we have, I'd say, a very promising system for studying the analog to cosmic string formation in the early universe. So here's again the piezo force microscopy image of the surface of yttrium manganite that I showed you at the start. This was taken by Martin Lilienblum, who was a PhD student in the group of my colleague Manfred Fiebig at the ETH. And now if we look in a little bit more detail, you see always we have these 6 regions of up, down, up, down, up, down ferroelectric polarization meeting at what on the surface looks like a point, but in 3 dimensions is actually a 1-dimensional line defect running through the material. We don't have imaging in 3 dimensions, but here's the simulation I showed you earlier to give you a representation then of how when point intersects the surface, it might propagate into the bulk and then come out on another surface. Shown here. Okay, so I hope I've persuaded you then that we have a lab-based analog to the proposed formation of cosmic strings in the early universe. In the early universe, the proposal is we started from a high symmetry vacuum, and during the grand unification transition, a low symmetry vacuum was formed associated with the formation of cosmic strings described by a Mexican hat potential. In yttrium manganite, we have a high temperature paraelectric phase. We have a structural phase transition to a ferroelectric phase described by a Mexican hat-like potential, and that should be associated with this formation of 1-dimensional line-like defects. So now we'll use our yttrium manganite to actually run the experiments that cosmologists would like to do on the early universe. And I should point out that this is actually a little bit, you might think this is a little bit wacko. Remember we said at the start that one should be using a probe that's of a similar energy scale to the property that you want to study. And the grand unification transition is up here at 10 to the 15 gigaelectron volts. We already discounted the Large Hadron Collider at around 10 to the 4 gigaelectron volts. Now we're going to use multiferroics. If we look at the temperature scale rather than the electron volt scale, we see that our phase transition is at around 1,000 Kelvin. And so we're kind of sticking our necks out a little bit to think that we can use some process that's many, many orders of magnitude away from the process that we want to study. But we'll give it a try. Okay, so which experiments would our cosmology friends like to do on the early universe? So they said, well, we'd like to expand it at different rates. We'd like to go to the Big Bang, expand the early universe at different rates, cross the grand unification transition, and see how many cosmic strings form in the different cases. And we can't do that, but instead we can cool yttrium manganite at different rates through the structural phase transition, and we can count how many of these domain intersections form. And remember, what we're expecting is that if we expand slowly, there's time for different regions to communicate their choice of angle. We'll get large regions of the same choice and a low density of cosmic strings, or the other way around. If we expand quickly, there's not much time to communicate the choice of angle. We'll get small regions of the same orientation and many cosmic strings. So let me show you then what happens when we cool yttrium manganite at different rates through the 1,000 Kelvin phase transition. So this scale bar here in each case is the same. It's 4 microns. I didn't just take this one and blow it up. And these 3 images correspond to the 3 most readily accessible experimental cooling rates. In one, we heat yttrium manganite above 1,000 Kelvin, switch off the furnace and leave the sample in the furnace. In one, we take the sample out and put it on the lab bench. And in the last one, we take the sample out and put it in liquid nitrogen. And so you can see that we got extraordinarily lucky with the details of the materials physics of yttrium manganite, that the various parameters controlling the phase transition give us measurably different defect densities for readily accessible experimental cooling rates. We're, of course, not the first people to have thought of trying to study early universe transitions in condensed matter systems. It's a very intriguing idea. But the chances of, first of all, finding a system with the right symmetry and of it being cooperative enough to give you observably different densities for the experimentally accessible range of rates is really, really quite small. So we got very, very lucky with our yttrium main. So then, of course, one can have an undergraduate research intern sit and count how many domain intersections one has in these different cases and really plot the defect density as a function of the cooling rate. And so we did that, of course, and I don't have time to go into the details of this, but there was actually a really quantitative prediction of the domain size as a function of this tau q here includes the cooling rate and a bunch of kind of constants and parameters. So one doesn't have to just look at whether one gets more or fewer defects formed. One can actually really make a guess quantitatively whether the scaling behaves as predicted. And this is called Kibble-Zurek scaling. The quantitative part was introduced by Wojciech Zurek at Los Alamos National Labs. And for the case of yttrium manganite, here we actually used a very close relative, erbium manganite. One can calculate all of these parameters. One knows the scaling from statistical physics, and one can calculate what the proposed density of these vortex intersections should be as a function of cooling rate. And so the red line is what one calculates. This is a prediction, if you like, from early universe theory of how many domain intersections we should form in yttrium manganite, if the description is correct. And the red dots and the red stars are data points from two different groups, from the group of Manfred-Fiebig at the ETH and the group of Seng Chong in Rutgers. And you can see that there's absolutely remarkable agreement. So this was unconditionally exciting. I hope I can convey to the young people that it's unconditionally exciting to find actually that occasionally one is right, or not one's predecessors were right in their prediction and one's been able to verify it. So we have really, I think, in our multiferroic yttrium manganite, the first example of Kibble-Zurek scaling, this proposed physics of cosmic string formation in the early universe, really in a solid state sample that we can study at the lab bench, that sits there, it doesn't go away, it doesn't care if we lose power even, it's a very robust crystal sample. It was very amusing to me. So we work with these multiferroic materials, as was mentioned earlier, lots of potential technological applications. We can design exotic new devices. But this kind of esoteric application of thinking, can we use them to study early universe physics, really captured the public imagination much more than there was much more interest than in having a more faster computer or a more powerful iPhone. And I loved this article in the National Geographic that the universe's existence might be explained by our new material. A new material could help physicists explain the existence of matter, such as this astronaut seen above the Earth. I think this might be overstating things a little bit, particularly when I show you, in the interest of full disclosure, that we're absolutely not all there yet. Which, of course, to a scientist is the most exciting thing. If we had finished, if we had completely the answer, we'd be done, and there'd be no more fun to be had. But we actually have many things that we still don't understand. So here is some more data, then. The same plot, the vortex density is a function of cooling rate. And remember, this is what we saw before, these lines, these straight lines, which we agreed rather well with the experiments. What we see are two things which we don't understand. We see at very fast cooling rates this turnover, which we don't understand. We have some models, which we rather like, which are consistent with this turnover, but we don't know which ones are right. So we still have a lot to do to understand that. And we see this dependence on the chemistry as we change the rare earth cation. which is also completely unexpected. So this is now the forming the thesis research of the next student working on this problem, Quintin Meyer, who tries to understand whether this turnover is something real and intrinsic, whether it's relevant for early universe physics, or whether it's because we have just junk in our system, and whether it's just a kind of artifact of trying to do fundamental physics in a material system that has all of its associated problems. Okay, so I hope I've shown or persuaded you that our multiferroic materials really do provide an example of the proposed mechanism for early universe phase transitions. And a little bit tongue-in-cheek, I can say that cosmic strings really formed the way that cosmologists think, at least to some extent. And I hope I've persuaded you too that using condensed matter systems to study questions from other areas of physics is really, really a lot of fun. It's really a very exciting area of research. I'm going to finish with this wonderful quote from an article in The Economist, which reviewed various approaches to doing, they called it tabletop astrophysics. And there's a wonderful quote from Cliff Burgess at the Perimeter Institute in Ontario, who's uncertain whether all our ingenuity actually unravels any cosmic truth. But he thinks such experiments are worth pursuing. Like tap dancing snakes, he says, the point is not that they do it well, it's that they do it at all. So thank you very much for listening. I'll leave you with this beautiful picture, again from the group of Manfred Fiebig, of the domain structure in a larger area of yttrium manganite. And I'd be happy to take any questions or comments or hear any objections that you have. Thank you.